We're going to start with a very, very simple example. This example it's called classification. We're going to try to figure out how to determine if a picture is of a muffin or of a chihuahua. So one of these pictures is of a muffin and one is of a chihuahua. That's a hint. Who of you thinks that this is a chihuahua? That's a very intelligent crowd. What made you think that that was a chihuahua? Okay, the eyes, the ears, the nose. Anyone else? Experience. Excuse me?
Didn't look tasty.
Oh, it didn't look tasty. Yeah. So I think all of that, but mostly experience. Because the reason why you know this is either because you've seen enough chihuahuas, or maybe more likely you've seen enough muffins to know that that was not a muffin. And if we do this, like if we were to do this classification with traditional development, it would look something like this. And apart from the fact that I can't spell chihuahua, and that picture contains is extremely hard to write without machine learning, this is also not a very useful piece of code, especially when you're faced with this. Because suddenly all the rules don't make sense. So what do we do instead? Well, instead we go and try to make machines learn like humans do, through experience. So we give the machine a large number of pictures of muffins and say these are muffins, and we give it a large number of pictures of chihuahuas and say these are chihuahuas, and then we have the computer figure out the pattern. And we can help it in different ways by telling it, I think you should use this method to find out what the pattern is, and that kind of stuff. And that is all that machine learning is. But it turns out that if this is the only thing you want to do, that problem is already solved. That problem is solved, for example, with Azure Microsoft Cognitive Services. So with Microsoft Cognitive Services, you can do things like call the Vision API, pass in a picture of a chihuahua and get out, it's cute, it's white and brown, it's a dog, it's indoors, and all that kind of stuff. No need to learn anything about machine learning. I'm just pointing this out because a lot of these problems are already solved. And you don't have to solve every single machine learning problem out there. You don't even know how that works. You can just kind of use them for a lot of things. And then, of course, there are other things that you can't do that with, and that's what we're going to talk about today. So if we look at a number of machine learning problems, like face recognition, that's a solved problem. There are APIs out there for doing that, also in cognitive services, but also in a lot of other APIs. Sentiment analysis. If you're selling a new phone, you want to know if it's top-notch, and you want to see what people thought about it, then you can have your Twitter feed sent through sentiment analysis and figure out, were they positive or negative? Was this person in this picture smiling or not? Also solved. And then we have things like figuring out what the stock price is going to be next week for a particular stock, or if this is a fraudulent transaction, or in Netflix, for example, what movies should I recommend to this person based on other movies they've seen or based on similar people. So recommendation, those are things that we actually do have to solve on a case-by-case basis. So we're going to go through a simple machine learning example manually, so you can see kind of all the steps. So apart from being a developer, I'm also very interested in houses, like I think 90% of the Swedish population. Haven't bought a house in 10 years, but I've been to enough showings that I have gathered a lot of data. And I'm not just saying this because this is like, yeah, right, she's just picked something up from the web. I've actually sat down and gathered a lot of data in Excel about sales in my neighborhood. I didn't know what I should do with them, but now I have a purpose. I can do machine learning on them. So what I've done is I've taken a lot of houses and I've said, okay, so these are the square meters the houses are, and this is the price for the house. Obviously, this is a very small subset. I've recorded a lot more data. But what I want to do is I want to figure out how much will a 150 square meter house cost. And the way to do that is to first visualize the data that we have, or try to make sense of it, and try to manually kind of look at what is it we have, so we know kind of what algorithms and things we should pick out. So I plot them out on a grid, and this particular thing, when you plot the dots, is called a scatter plot. You might have used this before in Excel or something. Like, it's a very common way to plot data. So here, for example, it's a 134 square meter house, 5.5 million, give or take. And then we plot all of this out, and now we have kind of like our data figured out in a way that we can see what's going on. It seems like the higher the square meters, the higher the price will be, roughly, right? So now figure out how much will a 150 square meter house cost. Any takers? No one? Yeah, like 6.2-ish, kind of. How do we know this? Well, we know this because we can do something. We can apply an algorithm and create a model. So we can draw a straight line that kind of approximates the data. We squint a little bit and it kind of looks like a straight line. This straight line is called linear regression. It's one of the algorithms in machine learning. There are plenty of algorithms, but this is probably the most easy one. And kind of making it into the, like fitting it to the data is called fitting the model. And then, by the way, just a tangent, I noticed that I wrote this value down wrong, so I had to clean up my data before doing this. So that's also a big part of machine learning, kind of cleaning up your data and making sure you have the right data. Okay, so now we have this, we have a model, and we can actually use this to figure out the 6.2 that we were looking for. All of this you can do in Excel if you just have two values like this. It's not magic. We'll look at how it's done if you have a lot more features and things. So the next step is figuring out, okay, so we know that this straight line is obviously not exact. It's not going to be every point ever, because this point didn't fit, this didn't fit, up there, they're even more off, because obviously there are other things that will influence the price of the house rather than the square feet or square meters. So to figure out how bad or good our model is, we just use a highlighter and draw across all the dots, and then we say this little envelope is called a confidence interval. This is like how good or how reliable our model is. So for this, for example, we can say, okay, so I'm guessing 6.2, but it's going to be somewhere between like 5.7 and 6.8 maybe. That's our confidence interval. And this is also a very important part of machine learning, kind of figuring out how good or bad the model you create already actually is, to find out what confidence you should have in it, and if you need to refine it to make sure you have a better confidence. So we've gone through the whole process of machine learning. We started by asking something called a sharp question. I say sharp because it has to be a question that's crisp and that can be answered with the data. You can't just say, what do you think the house market is? Because that has so many answers. Instead, we need to ask, like, what's the price of a 150 square meter house? That's a sharp question. And then we collect the data, we explore the data, we drew it out on the scatter plot, we clean it up a little bit. We haven't done any feature transformation, we'll get into that a little bit later, but we selected an algorithm, linear regression, or straight line. We trained the model, we kind of fit it in the right place. And this whole fitting is easy for us as humans, but for machines it has to do with a lot of math, like figuring out how the line should look. And then we use the answer. And this is actually a very important part, because sometimes you kind of get stuck into doing the model and then you never get around to actually using the answer. But we're going to go through all of these in a little bit more detail. Good so far? Okay, so asking a sharp question. turns out that there are only 5 questions that machine learning can answer. Kind of not 5 individual questions, but 5 types of questions. And the 5 types of questions we have are how much, how many, something that gives you a numeric answer, like how much does this house cost, how much is the stock price, what will the temperature be on Thursday in Stockholm, how many people will buy this product, that kind of stuff. And then we have, so this is called regression, and this kind of part of like the whole linear regression comes from that. And then we have the next question, which is it this or that, or the other thing? So classification is about figuring out what class this belongs to. Is it a chihuahua or a muffin? Is this spam or ham, like this email that just came in? This person with these kind of symptoms, is she going to have diabetes or not? Is this news article about music or technology or politics or whatever? So a lot of things that you can do to classify different data. Is it apples or oranges? And then we have a special type of classification that's called anomaly detection, where you ask, is this weird? So, for example, is like in all of these good transactions, is this particular transaction fraudulent? Or in my log of internet requests to my web server, is this particular request weird? And the reason why why this is separate from classification is because in this case, the class of good or bad are so different. Like there's this minute amount of fraud transactions compared to real transactions. And there is a small amount of weird requests compared to good requests. So you use different algorithms because the regular classification algorithms don't work. And then we have which groups. So this, up until this point, we've been talking about something called supervised learning, where we have the answer in the data. We have a list and table that has house prices given a set of input, or of these. Whereas this one is called unsupervised because we don't know what answers we want. So it's kind of like classification, but for example, we say break these products into 5 product groups. Like so, if you would say break them into laptops and phones and whatever, it would be classifications. But in this case, you're just going to say break them into 5 different groups that seem similar, but I don't know what those groups are. I just know I want 5. And when would you want to do this? Well, one example would be, for example, if you want to figure out groups of products that seem to belong together, that people seem to want to buy together, or things like that. That might be a reason. Like type of movies that people that like one might like the other ones, which kind of this part. And then finally we have something called reinforcement learning, which is which action should I take? So for a robot vacuum, for example, should I keep charging, or should I go on a vacuum? Or should I raise or lower the temperature in a temperature system? So the way this works is way different than the other ones, whereas the other ones, we kind of predict them beforehand what's going to happen, and then we use that answer. In this case, we kind of start doing something, and then we get positive or negative reinforcement that tells us do more of that or do less of that. So think about, for example, if you have a kid that touches the stove and then burns himself, and then you say, okay, so he's now learned that that's not a good thing to do, and will stop touching red hot spaces. Whereas if he gets like positive reinforcement, like, oh, you did a really good thing here, keep drawing, keep doing this or whatever, then he's going to keep doing that. So that's kind of like how reinforcement learning works. Okay, so then we'll go into, so now we know the questions we're going to ask. Now we're going to go and collect the data. And obviously there are plenty of ways to collect data. In this very building, we have monitors or motion sensors under a lot of the shares, not in this room, but or under a lot of the tables that tell us if someone is sitting there, if someone is entering the bathroom, that kind of stuff. And we use that for facility management, and we can use that to do machine learning on how often should we clean the bathrooms. Do we need to make changes in our air conditioning and stuff like that. But when you start out, you might want to start out with something not that complex and start out by doing like sample data. So you can, for example, with the house case, you could technically screen scrape Hemnet or Booley, and they have a lot of data on sold houses. You're saying, not that I've done that. And then there's like a lot of sample data sets on Kaggle. Kaggle is a competition site for machine learning with a lot of free data sets and a lot of knowledge about how you do machine learning. So a good place to start if you want to have some data to start out with. UCI is also a free set of data, like basically companies that have donated their data. It's old data, so you can't really do a lot of good useful predictions, but it's a good place to kind of get your mind around what you can do. And then I'm going to show Azure Machine Learning, and Azure Machine Learning comes with its own data sets, like sample data sets. Yeah, it's a couple of samples of what you can find, like who survived the Titanic, how good are these wines, 800 UFO sightings, if you're interested in doing some machine learning around that, would be interesting. But independently of how you get your data, you're going to want to have it in a table, kind of like an Excel type table. So even if you have it in multiple stores, like if you have it in multiple tables, you have to kind of join them into one single table. And that one table, and this is kind of specific for supervised learning, you're going to have something called a target. So the target is what we're trying to predict, in this case the house price. And then you're going to have a bunch of other columns, and they're called features or input. And each feature is sort of like something that has something to do with the house price, like the area may affect it, if it's a townhome, like a radhus or a villa, or where it's located, that kind of stuff. So those are all features. And part of the trick is finding good features that will actually make you help predict the answer. And each row is called an instance or an observation. And each row then has to have the target exactly once. So far, not too difficult. Now, each one of these features can be either a number or a category where it's either a house or a townhome, or it has a few different types of values that it can have. Or it can be something like a zip code that kind of looks like a number, but it's not. It's actually a category. And the reason why that is important is because if you tell an algorithm that this is a number, it will do things to it like compare, is this higher or lower than this one? Then maybe it's better or not better, which doesn't make sense in this case. And it will try things like multiplying and dividing and subtracting and things. So you need to make sure that if you have numeric things that aren't really numeric, you mark them as categories. So when you pick your features, there are a couple of things you want to look out for. You want to have features that are relevant. So a relevant feature might be how far away from the water the house is. That is at least relevant for me. Something less relevant is like the number of chickens in Alabama the date the house is sold. It kind of obviously has no importance. And then you might run into things where you don't necessarily know if it's relevant or not. The broker that sells the house, they like to play up their importance a lot, but when I've done my data analysis, it's not so much so. But one thing about the broker that I found interesting when I've been analyzing this type of data is that sometimes the broker doesn't affect the price so much as the broker chooses houses in a different price range, houses in separate price ranges. So you might want to be wary of the cause and effect of things. So relevant is number one. Then they have to be independent. The machine learning word for not dependent is multicollinear, I think. Yeah, almost. So what do I mean by independent? I mean that, for example, if you have the area of the house in square meters, does it make sense to also have the area of the house in square centimeters? Probably not, because it's not going to give more information about the house. In fact, a lot of times it will ruin things because it will put too much emphasis on these similar type of things. So this is pretty obvious, but what about, for example, the number of rooms? The number of rooms in the area are usually very, very collinear. So they kind of describe the same thing. So for some algorithms, you might want to choose one or the other. And then they have to be simple. And simple means, for example, if you have the GPS location of the house, that's a pretty interesting thing to have. But what is math going to do with that? How is math going to know that this is better than another GPS? It doesn't know. So a better way to do that is, and now here is the feature transformation, is to transform that into, it's 10 meters from a lake. Because 10 meters from a lake is something we can compare to 100 meters from a lake or something, and decide that one is better than the other. So relevant, independent, and simple. So now we have the data, and now we're going to explore it. And ways to explore it, I've already talked about Excel. I'm saying that because most of you have probably used Excel. In machine learning, you often end up using either Python or R as the programming language of choice, because they have a lot of modules to draw data and to actually machine learning algorithm modules too. So this is an example of something called a Jupyter Notebook, where you can, in the browser, write Python, and then you execute it, and then you put markdown text and execute it. So it's kind of a nice way to go through and describe data. So if you're kind of curious about that, you can install that with something called Anaconda, or it comes with Azure ML, which is this, or it comes with Azure ML Workbench, or it's everywhere. It's like you can even put them in GitHub, and it will execute. And then in the middle here we have Azure ML, Azure Machine Learning, which is one way to do machine learning. A lot of people will do it with only Python, and Jupyter Notebooks or use Python by itself. We're going to take a look at how it works in Azure ML, because Azure ML is kind of nice when you start out, because it's a very drag and drop kind of thing. Okay, so we have the data, and to explore it, the way we explore it is we go through what we have, and we figure out, like for each of the variables we have, we figure out what type it is, numeric or not. And in this case, I had a few strings. If I have a string, I have to turn it into something numeric or not. And same thing with a date for the algorithms to kind of figure that out. And then we kind of mentally think about, like, what are our expectations of this feature? Do we think it will affect it, or do we think it won't affect it? Because we might want to just remove some features, because having a lot of features doesn't necessarily mean that we're doing better machine learning. Sometimes they just add weird noise. And then we go through and we look at the data that we have, and we look for a few different things before we clean things up. So duplicate observations means, for example, if we look at house data from Booli. I'm sorry if you're not from here, but Booli is a site where you can see all the house sales. And Booli, for example, has houses sold both the time they are sold and when they're transferred to the new owner. So you have 2 instances of each house, and you need to clean that up, because otherwise every house is going to count twice, or at least some of the houses are going to count twice. You want to clean up irrelevant observations. So if we're looking for creating a model for just houses, we might want to remove all the townhomes or all the apartments or all, because maybe they skew our line, so to speak. And then we look for things that are called outliers. And outliers are weird type of observations. Like, for example, if you have data that's, like if you have a very big house, but it's sold very cheap, that is not the norm. So you want to clean that up, because that anomaly can cause your model to kind of predict differently. And then you go through and look for missing data. So a typical missing data in the house case is not all the houses have a monthly fee. Like only bostadsrätt have monthly fees. So for all the other ones, like we had null values and needed to put in zeros instead. So you go through and figure out what are you going to do about when you don't have the data collected, and why is it not collected. And then you go through something called structural errors. So in the case of the houses again, if we look at the region where the house was sold, the realtors like to put in a lot of different things. So they might put in Östermalm, but they also might put in Stureplan. But Stureplan might be Östermalm, so you might want to kind of group them together to make a more coherent, like a list, and smaller list. Yes?
So, do you use any tools for this cleansing?
Yes, so for all of this, basically Jupyter Notebooks is really good. Azure ML can do it too, so yes, definitely tools. Tools, but also a lot of manual labor, but you can do it in Excel too if you want to. Yeah. Yeah, so for example, for the outliers, specifically what you do is you find out, you can draw it, like you can do a scatter plot like this one, and you'll see here, this one looks super weird. Everything else has an area of 300 or less, and then this one comes in at like 500, that is like, and it wasn't very expensive, so then I'm gonna say, okay, so for every instance that I have over 300, remove that. And there are very good tools in Python, in Pandas Pandas is a module that you use for doing that specific thing. But you could also filter it in Excel and remove that line if you, like the tool of your choice, like the tool doesn't really matter. Yeah, so you use this to do the outliers. By the way, this is the same data we looked at before, but a lot more. In the previous plot, I had picked just houses right around my house. This is like all the houses in Sollentuna. So the spread is a lot more because the houses cost a lot different depending on where they are and so on. So you do things like that, and then you also do things like, this is a correlation plot. We're not going to go through a lot of plotting and stuff, but what something like this is doing is it's telling me the more red something is, the more dependent they are. So the price depends a lot on the area. It depends a lot on the land area, but it's negatively dependent on the monthly fee. So that means that as the monthly fee goes up, the price will go down. And the more red it is, the higher the correlation, and the less red it is, the less the correlation is. Okay, so that was enough statistics and math for this class, I think. So then you've gone through this and you figure out what you're going to do. So you fill out, okay, so remove everything that's over 500. In this case, I might say, if it's a monthly fee, I might say I'm going to even add another column that says, this is a condo, this is a bostadsrätt, to be able to filter them out later or something. Or for dates, I might split the date into months sold, because maybe it's the case that if you sell houses in July, they will cost less than in September because there are less people. I don't know. At least I'm going to be able to look and see what the difference is. And then I go through and clean the data, basically perform all the tasks that we've said. So we're going to look at a different data set. This is a very important data set of bunch of superheroes and whether or not they wear capes. So obviously the most important prediction of the year. But what we have here is an unclean data set. So we have some names and some IDs. We're going to remove those when we do the algorithm, because while they're interesting, kind of, they're not going to reflect, like they're not going to be able to use as predictors for whether or not they wear capes. And then we go through and see the year they were born. It looks really ugly because someone put it in and they didn't necessarily use the same format. So we'll go through and clean that up and put this in a nice similar format that can be added and subtracted and whatnot. Now the height kind of looks nice, but the problem with this is that it's American and they're not using the metric system. So it's kind of useless because you can't really add and subtract things. I don't know how they do it. So what we want to do here is we want to create a format that we can actually add and subtract. So we'll change it into inches instead of feet and inches. And then birthplace we'll leave as is because there is different categories. It's okay to have something like this, an unknown, because unknown is also a category. Unknown or other or something. You can use that as a category for things that you don't know, as long as obviously that wouldn't be a super good predictor, but at least it tells you that it's something else than the known ones. And then for this one, we have a few missing values, and we have some uncleanness. So we're kind of going back to whoever wrote this down, figuring out what does a missing value mean, what does NA mean. So NA means no, it's not secret, and so on. And we'll clean that up. Welcome. Same thing with can fly. Alignment, here we have 3 categories, good, bad, or neutral, because Selena Kyle is neither. And then whether or not they wear a cape, same thing. So this is kind of like the tedious part of machine learning, cleaning up the data to a format where you can actually use it. Sort of, some people call this shaving the yolk, because yeah, I like this part, but it's very, very tedious. Okay, so once we get here, we can now go through and do something we call transform features if we need to. And transforming features is what we talked about with this GPS. For example, where the GPS location is not very usable, but instead, like a location or a distance from a lake would be usable. So transforming features means taking something you have and transforming it to something that would actually be useful. And in this case, the GPS system or the GPS coordinate may even give you a number of different things. You might be able to say how far from a lake, how far from the most common schools, how is this like on, what do you call it, like right by the E4, because then you don't want to have that house, and that will kind of degrade a house and stuff. So, so just using a feature that you have and turning it into something more useful. Another example, if we're looking at sales of ice cream and you have dates, then you might want to turn it into, is it winter or summer? Because that would be a useful feature. Or is this a vacation day? Because then people will buy more ice cream and that kind of stuff. So transforming features. And now we're finally getting into like the machine learning bit. So far we've just been doing data science, but I have to say, once a lot of cases you might end up with a situation where you've done all the data sciencey bits and you've already found the answer. You don't actually have to create a model because you've gotten enough information from the data that you can sort of answer your stuff on your own. But selecting algorithms, so we're going to look at a few of them. We've already seen linear regression. Linear regression is not necessarily used by itself that much because it's a bit rudimentary. But what you can do with linear regression is you might turn it into something called lasso regression or Bayesian regression or ridge regression, which is a way to use linear regression, but where it selects the features by itself a little bit. So this is kind of like a base algorithm, and then other algorithms are built on top of it. Another one, there's also a base algorithm, is called a decision tree. So what we're going to look at here is we're going to figure out whether or not people will play tennis today. So figure you have a store of that sells tennis stuff or that has tennis courts, and you want to figure out, do I have to have a lot of people in the store today or not? That's kind of the question you want to answer. And you have this data about, do a lot of people play tennis given these conditions? So we're going to use something now called a decision tree, and a decision tree is a little bit like asking 20 questions. You know, when I'm thinking of a person, and then you have 20 questions to figure out what I'm thinking about. So if I'm thinking about a person, what would you think what would your first question be?
Male or female?
Yeah, obviously, male or female. Because, why?
Well, depending on what's normal for you.
Probably because it splits the amount of choices in the biggest part, right? Because then you kind of eliminated half the population. So that's what we're trying to do in decision trees. We try to kind of split them up in such a way that we get like the biggest chunk, so we can make the biggest determination about the data. So let's see how this looks. In this case, we want to figure out if it's a yes or a no. And this is our data. I've colored the ones that are yes. So is there some question that we could ask that would immediately kind of give us the answer? Temperature? What about the temperature? Yeah, so for example, for hot, in some cases we have hot, no, hot, yes. And in some cases we have cool, yes, cool, no. So that wouldn't necessarily really do anything. But take a look at this one. Overcast. If it's cloudy, then in all given cases, people will say yes, right? So we can have a question that says, what's the outlook? If it's cloudy, then immediately we can say yes. This is kind of like if statements, like that's all decision trees are. And then we say, okay, so what about the other cases? So if it's sunny, what can determine if it's good or bad then? I think now is when your temperature comes in. So here, for example, we have if it's cool, then we definitely know it's a yes. Let's see what I picked. So, I picked humidity. So if the humidity is high, then we don't play. If the humidity is normal, then we do play. And same thing for if it's windy. If it's rainy and windy, then we don't play. If it's rainy and windy, then we do play. So these are yes-if statements. So this is the plain way a decision tree works. Now, you don't normally put a decision tree by itself. You put it in a forest. So a forest means that we have tons of decision trees, and then we have them vote or average things out. But at least you know kind of like the basics of what a decision tree is. Now, next one is called naive Bayes. A naive Bayes works like this. We have a bunch of emails. Some of them are spam, and some of them are not spam. And now we want to figure out which ones are. So we're going to look at a particular feature. I think if there's a spelling mistake, then we have all the spam emails have spelling mistakes in our case, and just like a few of the good emails have spelling mistakes. So we can use this, and we can say, okay, given that there's a spelling mistake, what are the chances that this will be a spam email? Sorry for making you do math in the morning, but it's 75%. And then we go through and do that for, like, if it contains the word sheep, or if it doesn't have a title, or a bunch of other features that we can figure out. And then we combine that all together using a formula. I'm not even going to put up the formula, but it's a pre-given formula. And that will tell us the percentage chance that this is a spam email or this is not a spam email. So this is called naive Bayes. And then finally, we have logistic regression. It has the word regression, but it's used for classification. So what this is, we're trying to compare apples and oranges. The green dots are the apples, and the orange dots are the oranges. So what would be a nice way to compare, like to figure out if it's an apple or an orange? Taste, yeah, that would be good. But for example, if we put a dot here, would that be an orange or an apple? Yeah, okay, so one good way, this is logistic regression, is we draw a line. We try to separate these out somehow. And we say whatever is above the line is now an orange, and whatever is below the line is an apple. And this line is kind of fit the same way that the linear regression is fit. Okay, so if the data looks a little bit like this, it's not kind of linear, then we can either use a decision tree or we can use multiple logistic regression. So we can kind of do the ninja thing and do like multiple kind of lines like that. And when you do multiple ones on top of each other, that's called a neural network. That's what a neural network is.
Can you have a curve?
Yes, so yes. Kind of not in logistic regression, but in other ones. And also what you can do if you have a curve, I'm not going to go into that super a lot, but then you usually look at the different dimension and see if you can find, because maybe if you add another dimension, not acidity and sweetness, but like color, then maybe you can separate them in 3D space with a straight plane instead, and things like that. Or maybe you can transform the features. If you have a curve like this and you take one times the other, then you get a straight line. So yeah, so you do a bunch of tricks to make it more straight. But there is, for example, for the logistic or linear regression, there's also polynomial regression. That's like second and third degree curves. So neural nets just means, okay, so we take this one, which is basically saying, is it above or below that line? Input like all our data in that and get the answer. And then we do the same with the other line. And then this is just an and. So if that is true and this is true, then this is true. Kind of is an and port that we're used to. Obviously, neural nets are not that simple. They're like this long and this wide. And the cool thing about neural nets is that we don't actually have to figure out the features. We don't have to figure out what this line is in all the cases. The cool thing about neural net and deep learning is that deep learning is used to figure out the features for us. That's kind of like the allure of deep learning, that we don't have to do this, a lot of this data cleansing and data figuring out and that kind of stuff. But yes. What should you use? Yeah, that's a hard question. But there are plenty of algorithm cheat sheets out there that will tell you, and I don't expect you to read this, but I'll just say, for example, if you're predicting a value, like a number, then you're in this one, and then depending on if you want fast training or if you want if you have a small data set or whatever you want, you might use different ones. In reality, the way it works is that you try all of them, and then you see, like you do something called spot checking, and kind of see which one seems to perform best, and then you start tweaking that one. So while you have an idea of which ones will probably be better than others, you're going to try like 20 or so before you're finished. Sorry, okay, so we're at a point where we're going to train the model and actually apply the algorithm, because choosing the algorithm doesn't really help us with the answer. So training the model looks something like this. You take the data set and you clean the data, And then you split the data into two different sets, or actually, as it turns out, when you get a little bit more advanced, you'll split them out in different ways to make more use of your data. But for simplicity, you split your data into something you train on, and you split the data into something you test on. Because once you've started doing things, like for example, this was the original one, I could have done what Alan was talking about, like doing a curve and figuring out like, okay, so it's going to be like this polynomial curve with a lot of ups and downs, and that fits the data perfectly. But then how do you know how good that model is? Well, the only way to know is to test it on something that the model hasn't seen, something that the model hasn't actually fitted itself to. And then you figure out, well, it turns out that a straight line on average will give a better prediction than this one, because when you do things like this is something called overfitting, and it's very, very common in machine learning that you kind of overfit. You make the model too perfect for the training set, but it doesn't at all apply to the testing set. And there are ways to figure out like where is the optimal kind of like the optimal number of degrees and things. You do things like training curves and lots of different things that I'm not going to talk about now, but just be aware that this is the major problem you're trying to solve in machine learning kind of. So we split the data into two, and then we say we go in and we train a model. You can do this in Python or in machine learning. We're going to look at machine learning, Azure machine learning. You pick an algorithm, and then when you train the model, you score it with the test data, and then you evaluate it to find kind of like that confidence interval or things like that. So let's have a look at how this actually looks. So first off, I'm just going to show, this is Jupyter notebooks running on my machine. The cool thing when you run it, for example, in Azure ML, is that you can use data stored in Azure, and especially if it's big and you want to do a lot of computations, then obviously it's a lot more powerful to be able to do it in the cloud with all the computing power that exists there. But right now I'm doing it on my machine. So I'm just running a bunch of commands, like all of these. This is just code, and I do like, I execute it, and this actually executes on the proper data set. So you use this to figure out like statistics about the features, like what's the high and low of this, how do they look, and you can then go down and, like, so here I've written in Markdown what I think about the features and if I should use them or not. This was what I was talking about with like how I should clean this later. And then do all the visualizations to see if it follows a normal curve, that kind of thing. Scatter plots. Here we have the 500 one. Here is how you actually go through and I didn't do the cleaning here, but it looks very similar to this when you actually go through and delete them. And that, here is the cleanup. Let's see. Never mind. Essentially, you would go through and do a lot of your stuff in here, and at the bottom you'll also see, for example, the correlation plots that I showed earlier. So this is a very powerful tool. And then we'll go through and do the actual experiment. And I should say, you can also do the machine learning in Jupyter Notebooks if you want to, but I'm going to show this more in a drag-droppy state. So the output of my cleaning was this houses in like a cleaned version of the houses. And then I'm going to go through and I'm going to do something called select columns. Because here I go and say which particular features I want. So I'll pick up most of them, but I'm going to leave, for example, the year and the month. I have something that I devised called a running month, which was just basically how many months since the start of the data, so I can compare like as time progresses, do things become more expensive or not? And then I go through and I do, I can edit metadata. And the reason I'm editing metadata is because of that thing I was talking about with the categorical features. So I want to tell the machine learning algorithm which ones of these are categories and not. So house type, for example, and the region, and then also is condo are categories. And I go in here and I say field or categorical, make categorical. So I'll talk a little bit more about what I'm doing. I'm just going to drag something out because I'm going to need to start running it since it takes a little bit. So splitting, train. If you don't want to actually search for things, you can go through and browse through the individual ones. So score. And I'm going to do this for 2 different algorithms, which is why I'm doing 2 of them. And finally, an evaluate. So you can see this looks exactly like the picture I just had on the screen. Now, what I'm also going to do is I'm going to pick 2 models that I'm going to use. And to pick those models, let's see, I'm going to here. Under machine learning, we're going to look and say, am I looking at anomaly detection or classification or clustering? No, I'm looking at regression. So from here, I can now pick 2 models. I'm just going to pick 2 semi-randomly. A boosted decision tree, so that's a decision tree that kind of builds on top of another decision tree and so on. And linear regression is like a special case of Bayesian linear regression is a special case of linear regression. So I'm just going to connect all the dots here. So to the training, I picked from the split data, we have the training data and the testing data. So I'll pick the second one to go in when I score it. And then I move all this to evaluate. Don't worry, I'm going to explain everything in just a little bit. And when I train a model, it needs to know what it actually is supposed to predict. So that's why the red dot showed up there. So price. Okay, so let's start running this. So now it's actually going to go through and do all these tasks and train the models for me. So again, I split the data. Oops, I think I didn't remember to put in the properties. But so right now it's splitting the data 50-50. Normally we would want to split the data maybe 80-20. So we have 80% for training the model and 20% for testing the model. Or we might want to do something called a k-fold split, which essentially trains the data a number of times on parts of the data using parts as testing, and then use other parts as training and other parts as testing, and so on. That way you can use like the whole data piece. And then it goes through and scores it, and scores it is essentially just using the model to predict all the values and figuring out how well it did. And finally evaluate and goes through and says, okay, so give me back the metrics, the what do you call it, like the confidence intervals and things. So let's see how this looks. So once you've dragged in the data set, you can go through and visualize it right here. So this is a way that you can properly do like all those scatter plots and everything too if you don't want to learn Python. But I suggest that you do learn Python or R. So again, if we look at the area here, and I'm going to say compare it to the price, it will actually produce one of those scatter plots for us over there. And here we can also get a good grasp of distributions of things, like for example the price here. How does that look? Well, it's kind of bell curved in the beginning, and then it has probably some outliers at the end and stuff like that. Now, we clean things up and we split the data, and then we train the model. And when we train the model, let's take a look at the decision trees and see how that looks. So you can see this has a lot of different decision trees that we'll use together to kind of average things out. But the decision tree looks very much like what I was painting on the screen, right? So you can't see this, but in the beginning it says land area less or more than 751 square meters. If it's less, go here. If it's bigger, go there. And then for all of those, if the area is less than blah, 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 then do this, and then it splits them out based on what it thinks it's normal. So a decision tree can also be used not only for categorization, but for finding a number, actually. But then you'll have to have something like this that kind of averages the numbers out. Decision trees are pretty nice in terms of like visualization and kind of getting an understanding of what's more important and not in your data. So now the next thing is, for example, when we score the model, if we'll, yes?
Thinking about the different trees, is it like random, like trying to pick a number of different features there as the top node to see?
Yeah, so depending on which kind of, it's called an ensemble when you use like decision trees together, but depending on which one you use, and I can't remember how the boosted decision tree works, but in some cases it picks only a subset of features and creates like different, a decision tree for this set of features and a decision tree for that set of features, and then it randoms it together. Or in some cases it just picks a number of data points and creates a decision tree for that, and then averages it together. Or, yeah, there are different, depending on, like they're called bagging or stacking or boosting, depending on how exactly you decide on the decision trees. But yeah, does that answer your question, kind of? Yeah. Yes, so here we've actually scored a model. So what we see here is the average answer that the algorithm gave. So in this case, it was supposed to be 6,100,000, and it came up with 6,700,000 as an average. Why is it that bad? I should have had more features. There are more things that actually influences the house, like the quality of the house. I don't have that feature, so when you get to this point and you want to get better at things, you want to go back and kind of figure out what could I do to improve the model. And then you go through and you evaluate them against each other. And here is sort of like the results of both of them using different types of criteria, like the mean absolute error, like how far off are we on average. And from here you start then going through and saying, okay, so it seems like the you typically look at the relative squared error and root mean squared error more than the actual mean squared error. So in this case, it seems like the top one is probably better than the second one. So then we start tweaking that and figuring out, should I use different features? Should I maybe change some of the parameters? How many trees I can use or stuff like that. But this is the whole like real machine learning process. This is like all there is, except for like the tweaking part. So how good is the model? Might be a good way to end this thing off. And I'm just going to look at 4 classification things. So this is if you predict spam or ham, like you get an email and say, is this spam or not spam? So there are a couple of different ways that you can look at goodness of a model. So first you have accuracy. Accuracy means how many you actually got correct, how many you put in the right box. So accuracy, you take all the ones that you got correct, 100 plus 700 is like 800, divided by the whole lot, which is 1,000, and you get 80%. In some cases, though, that might not mean anything because let's say you have fraud detection and you say, if I just say that anything is a real transaction, then I'm bound to get like 99.99% accuracy. But it doesn't necessarily mean anything because I didn't catch any of the bad ones, right? So then you want to use different ones. Precision, for example, is how many of the ones that we send to spam are actually spam. Like 100 out of 130. Like so, the ones you get wrong, like the non-spam emails that you send to spam, that is probably something you want to minimize in this case because it's super bad to send real emails to spam, but it might not be as bad to send spam emails to the real mailbox. You can always, like you're good if you're kind of like have a spam algorithm that filters out most of them and you have to do some manually. But if you lose that one email from your boss that was really important, that could make or break something. So determining whether or not you need accuracy, precision, or recall is something that you want to look at. And then use the answer. And I'm running out of time, but I'm just going to say, in Azure Machine Learning, once you're done with this and you've decided on a model, then you can take your trained model and create a web service out of it that you can actually call with new data. And you can create a model that you can put into Excel and just bombard with similar rows and get it to answer those for you in a batch format. So that's pretty nice. But yeah, that was the whole process of machine learning. So with that, I hope that you've gotten enough to kind of get excited about machine learning and to understand what it is people are talking about when they talk about machine learning. So thank you.